Talk about classes. So last time we introduced classes, we talked about a lot of new topics. We saw objects, classes, a lot of the keyword this, well, a lot more of that today actually. References, we reinforced references, our understanding of that. Let's continue with that. And we didn't quite get through the memory diagram. I think we saw one or two slides in this lecture, if that. So let's start at the top of the memory diagram and go through that. And I'm realizing we're not going to get through today's slides either. Actually, I knew that before the first lecture. We're not going to get through today's slides either, but we will get through this diagram and then about half of the next one. And we'll pick up the rest of the next one on Friday. So that's the plan for today. Let's do a lot of tracing. We're going to spend our day in memory diagrams today. So let's trace this thing. We saw this code last time. Let's jump into it. So the very first thing that we do is one of our new things that we haven't seen before. We're going to create a new object on the heap. Now we've seen this with array list and hash map, but those are two kind of special cases. We're going to represent array list and hash map a little bit differently than our other objects. All other objects on the heap we're going to represent in this format we're about to see. We're going to put a solid box separated into two columns, and just like everything else we've seen in memory, there's a split into the names of our instance variables and then the values in those variables. Then we're going to put the type of the object above the object on the heap and the reference to the object below the object on the heap. And so we're creating a new player. So we're going to get an object of type player and then a reference OX and then whatever number you want to make up. If you want to do OX1, OX2, OX3, OX4, that's perfectly fine. I'll choose 3-digit numbers for slides, and I just make them up. When I made this slide, I was feeling 999. So I put 999 for this reference, but it's just a made-up number. It has no intrinsic meaning. It just has to be consistent. Whenever I have a reference to this object, I have to match this reference, its reference number. But you can use any number you want for that. And then when we create a new object, this calls the constructor for that object. Constructors are method calls. This is a method call. Means, I forgot. So we're going to put the instance variables, the names. We don't have any values for them yet. Technically, they do get initial values from Java, but we're always going to be explicit about our initial values. And we haven't called our setters yet, so we're not going to put any values here yet. But the constructor is a method call, which means we got a stack frame. Constructor calls get stack frames. You have to make sure you put your constructor call stack frames on the stack. It's where they go. So just like any other method call, the constructor parameters are going to go inside that stack frame. We have name and max HP equal to the arguments. But we also have one additional value that's in the stack frame for any constructor call and any non-static method call. Really, any non-static method call and constructors are always non-static. We always have the value this stored in the keyword this, which is going to be a reference to the object that's being created. And then for our future method calls, it'll be a reference to what I call the calling object, which we'll see when we get to all the method calls. So when we create a constructor, the name of the method, just like any other method, it's the name, but the name has to match the class type, the class name for our constructors, parameter list, and this, a reference to the object that's being created. I made up this number. It can be anything, but it has to be the same in both these two places. It has to be the same value. So we know that this inside the stack frame refers to this object that's being created. As a notational note, I have two of these today where I'm going to start doing my memory diagrams just a little bit different. I'm not going to draw my reference arrows anymore. I do recommend that you still draw these on your quizzes to be very clear about your intentions. I'm going to stop doing these on the slides because I can color code my references on the slides to make it clear what reference refers to which object. But as we get into these memory diagrams, starting with this one, they're going to get more, I shouldn't say very, but they're going to get more complex. They're going to get bulky. And if I have all my reference arrows, it just looks awful. I've done these before with my reference arrows when we get to classes, and the slides just look completely illegible. So I'm not going to draw those arrows anymore. I do recommend that you do draw them on your quizzes still. On your quizzes, if you don't draw your arrows and you have one typo, if you have OX1 on objects OX1 and OX2 in the heap, and then there's a variable that should store OX1, but you write OX2. You just got one, you just wrote the wrong thing for whatever reason. We have to assume that you don't know what that you don't understand that code at that point. We have to assume that you meant OX2. We can't just say, they probably wrote the wrong thing right there. We're going to assume, we're going to assume the worst in that case. But if you write OX2 and you have an arrow pointing to the object with reference 1, then we can say, oh yeah, they just wrote the wrong thing. They obviously know what they're talking about because they drew their damn arrow pointing to the right object, making it very clear they meant that object, and they just wrote 2 instead of 1. So I recommend you draw your arrows to add the redundancy to make sure that you're not one little mistake away from losing credit. Add the redundancy so it's a lot easier for us to know that you do know your stuff on the memory diagrams. So I do recommend them for that reason. But I'm going to stop drawing them on these memory diagrams. Partly because I can color code them. If I couldn't color code them, that would be very confusing to read my memory diagrams, but I can, so it's not too bad. So alternatively, if you want to bring a box of colored pencils into your memory diagram quizzes and color code everything, by all means, go for it. No one's stopping you from doing that. So you can do the same thing that I do in the slides. So constructors, just like any other method call you create in a class, yes. It is treated a little special. It's called through the new keyword. The syntax is a little different. It's the only method that creates objects. But essentially in our memory diagrams, it's just like any other method call. For example, best key method that we wrote on the homework would be a constructor in the problems set Java class. Not best key. So you do have to match a couple key things. For it to be a constructor, it has to share the name of the class. It has to be exactly the name of the class. And it has to not have a return type. So if I put a return type of void here, I would get errors. I wouldn't be able to run this as a constructor. So if it shares the name, so if we created a method in our problem set class called problem set that didn't return any value, that didn't have a return type, then that would be a constructor in the problem set. But since best keys doesn't match the name problem set and it has a return type of string, it's not going to be allowed to be a constructor. So we can't actually say new problem. Well, we can actually. We can't really say new problem set right now because we don't have a constructor. We actually would get away with that because there is a default constructor. If you don't have any constructor, the default constructor of no parameters, no code in the constructor is created for you. So it would actually work, but it wouldn't have any non-static members. There would be nothing in it, so it wouldn't be super interesting. So every non-static method, which includes our constructors have to be non-static, or just methods. Again, if I just say method, I mean a non-static method, and I'll explicitly say static if I mean a static method. It's non-static methods almost exclusively from here on out, the rest of the semester. So methods take a hidden parameter of this. Every method is going to have this in its stack frame. It's important to have this with the correct reference in all of your stack frames for method calls. And a hidden parameter, it's just always there. It appears by magic. And for the case of a constructor, this stores a reference to the object that's being created. Then we call a method. This is where we see the calling object that I've been mentioning from time to time. This .setMaxHP. The dot operator means follow the reference to the object to which it refers. We're in this stack frame when this method is called. So this 999 dot means head over to the heap at 999. And at this player, when we're at this object, we're going to call setMaxHP. So the calling object, the object where we were when we called the method, that's the object that's going to be the calling object. So when we add setMaxHP to the stack, when we add the stack frame, this is a reference to the calling object. This is the object that called the method. So this is a reference to that object. And we pass maxHP. MaxHP is 10. From this stack frame, we pass it to this method. And we have this. Hey, I got ahead of my slides, so let me, not in chat either. So then we get to this line, this dot maxHP equals maxHP. So again, we follow the reference. This dot maxHP, that means we're talking about this variable in the heap. And we're going to assign this variable in the heap the value maxHP from the stack, which is 10. So we get maxHP equals 10. Bless you. So notice we have two variables named maxHP here. And this is where we use this dot. Some of you, and it comes up, and it's come up in like all three lectures, I think, in different lectures, all three sections in different lectures. But those of you who have used Java before and you didn't say this dot, you would just do this set max HP without the this dot, that can work for you, but not always. Right here we have two variables. I'll explain that a little more. Hold on, let me circle back to that. This dot max HP means this dot go to the heap and use this variable. If we just say max HP, Java is going to look in the stack frame for a variable with that name. So max HP, we're going to look in the stack frame. We're going to find max HP, which is 10. There's no dot operator, so we're not going to the heap explicitly. We're going to find this variable and use this variable right here. If you don't use this dot, since it always comes up, I'm just going to talk about it. If you don't use this dot, and I just said set max HP of max HP, we're going. What Java will do is look for a method named set max HP by following this dot. It's going to go to the object referred to by this and look for a method of that name. And if it finds it, then it's going to use that method. In this case, since max HP and max HP have the same name, if we did max HP equals max HP, we're not getting away with that one because we're using max HP without this dot. The search starts inside the stack frame, and it's going to find max HP and use that. If I name this something else, if I name these two different names and said max HP equals max HP param, if I name this max HP param, then max HP param not found inside the stack frame, so it'll follow this dot and then look for a variable named max HP in that object. So for those of you who didn't use this dot all over their code like I do, that's the shortcut that you were getting away with. But it can get you in trouble if there's a local variable matching the name of the instance variable that you're actually after. I'll always do this dot, except when I forget. Sometimes I make mistakes and I miss it. But I like to be as explicit as I can and use this dot all over the place to make it very clear that I mean I'm going over to the heap and doing something over in the heap. It makes my code easier to read. It makes my intentions very clear. If you see this dot max HP equals, you know that I'm changing the state of an object when you see that code. If it was max HP equals max HP param, it's not immediately clear what my intentions are there. So I like to add them, and especially when I'm teaching, I want to make sure everything's clear and not use those shortcuts, because I think it can be confusing. If you're going to the heap without seeing the dot operator, it's, how do I say, dot means follow the reference. It's harder to get those points across. And once you're comfortable with this stuff, you can stop using this dot and you'll understand what's going on. But when you're first seeing it, I'm using this dot every single time. And even outside of the classroom, I like to use it anyway. I like to be explicit in my code. So the second notation note, second and last one for the day, which I forgot to mention in the last lecture. When a stack frame ends and is removed from memory, for my slides only, I'm going to just gray out the stack frame instead of crossing it out. For your memory diagrams, you'll still cross them out, and when you see my grayed out stack frames, that means the same thing as crossing it out. I'm just going to gray them out for my slides to make again, just like removing the reference arrows, to make the slides more legible. When I cross them out, it's hard to read the variables underneath the big X, and I want you to be able to see all the history of the memory diagram as we go. So I'll just gray them out so you can still read what was in that stack frame, and just make everything a little cleaner. These memory diagrams can get very messy if I let them get out of hand. So I just use a few tricks just for my slides to keep them legible. I will always do my return arrows. I won't draw my reference arrows. I'll color code them, and I'll gray out stack frames and code blocks that are no longer in memory. And we'll call set HP. And we can see how these references move around the code. There's only one object, so it's always going to be the same reference at this point. But we're going to call set HP. This dot, so this is in this stack frame, this dot, set HP. So it's called from this object. So this in the method call is going to be the reference of that object, OX999. HP was max HP from this stack frame, which is 10. And we're going to do a comparison if HP is less than or equal to this dot max HP. So HP, we're going to look in the stack frame. We find a variable named HP and its value is 10. This dot max HP, this dot max HP is 10. So we got 10 less than equal 10, true. So this dot HP equals HP in the stack frame. So again, we have two variables named HP, and whether we do this dot or not is going to determine which HP variable we want the value of, or which one we want to assign. And same thing for name. I don't have much else to say about that one. With strings, actually, I guess I will say this now. With strings, we are going to pretend that they go on the stack, that they're stored directly in variables. This should bother some of you. It bothers me a little bit too, but it's better than the alternative for 116 at least. Any type that starts with a capital letter, that's going to be a type defined by a class, and we're going to create objects of that type, and those objects are stored in the heap. For any of these types that start with a capital letter, or more specifically, anything that's not one of our primitive types, it's going to be stored in the heap and passed by reference, assigned by reference. We're going to pretend in CSE 116 that strings don't behave like that they are just stored and passed by and assigned by value, because in effect, that is the way they behave. So we're going to put our strings on the stack just directly in our variables, even though technically they don't work like that. But it's going to really, really simplify things and clean up our memory diagrams by a significant amount. And then in 220, your 220 instructor will straighten you out and tell me, and they'll say, Jesse's a dummy. Why is he putting strings on the stack? It's not how they work. And it's not how they work. But it cleans things up for 116, because we got a lot of other stuff we want to talk about. And then in 220, they will want to talk about exactly how that works, so they can talk about that in that class. We got other things we need to talk about in 116 to even get you to the point where that matters. So we will put our strings directly in our variables as though they were passed by value and assigned by value. Exactly the way they behave. I shouldn't say exactly, but it's effectively the way they behave. To us, they'll behave exactly the same way as primitives. And then the constructor call, what a constructor returns is a reference to the object that was created. So this constructor call resolves to OX999 in this case, and that is what's stored in P1. So the constructor returns 999, and P1 just stores the reference to the object. P1 does not store a player object. Does not store a player. It stores a reference to a player, which seems like a subtle difference, but in our memory diagrams we can see how big of a difference that is, and we'll see why that's such an important difference. This whole object, This object is not stuffed into P1 right here in the value. The value of P1 is just a reference to that object. Now, I'll quiz you a little bit. What happens on this line? I'll pause for a second. You can, if you want to think about it and stare at it for a bit. But what happens on this line where we have player P2 equals new player? Yeah, sure. Yeah, exactly. So we're going to do the same thing, and I didn't want to click through this on the slide, so bam, there it all is. It's going to do the same thing that we did for P1. We're calling a constructor. We're creating a new object on the heap. We're setting it to different values. We got Cain and 14, and we're going to go through all the setter calls, the constructor call. The constructor returns a reference to the object that was created. When I made this object, I was feeling 820 for some reason. And that's what's stored in P2. P2 stores a reference to that new object that was created. Now, quiz you again. What happens on this line? We're saying player P3 and initializing P3. Yeah. Yeah, exactly. Yep. So I hope it doesn't do the same thing again because I don't have enough room on my slides. What actually happens here is it's assigned by reference. So, and this is one of the common mistakes. You'll get a quiz next week that's going to have a question that's going to be similar to this, in that we're going to test your understanding of references. 100%, you can guarantee that. It's going to test the, unless Paul messes it up. He's the one who writes the quizzes, so it's his fault if it doesn't. But this is an assignment by reference. P3 equals P1 means we're creating a variable P3 and assigning it the value of P1. So what's the value of P1? It's literally what's written in the value column, OX999. That's it. We take that reference, we assign that to P3, period. That's it. That's all we do on that line. We do not create a new player object. If you see the word new, you're creating a new object on the heap. If you don't see the word new, you're not creating a new object on the heap. So when you're tracing through your code, track how many times you hit the new keyword, and by the time you get to the end of your memory diagram, check your heap and make sure you have that many objects. We'll hit new twice in this. Set name isn't going to call new. Get name isn't going to call new. There's no new up here. We call new twice. By the end of our memory diagram, we'll have these two objects on the heap, and that's it. So it's a good sanity check. You get to the end of your memory diagram and say, okay, how many objects do I have on the heap? How many times did we hit new? They better match. It's a one-to-one correspondence. They better match. A lot of students getting this as a quiz are going to have 3 players on the heap. And that's a pretty easy one to grade. We just put a big X through it and say, you didn't pay attention to this lecture. There's no 3 players created on the heap. You got 2 players, and P1 and P3 refer to the same player object. A very important difference. And this is why references matter. If P1 stored a player itself, and this was assigned by value, when we say P3 equals P1, we would make a copy of that player, and there would be 3 players in this program. Since it's assigned by reference, there are only 2. Like, for example, if this were ints, if I said int x equals 7, y equals x, there are 2 separate ints in that program because that int is assigned by value. We don't have references to ints. But here, these are references to objects on the heap. So we only have 2. We have 3 variables of type player, but only 2 player objects. I'd say when it comes to references, that's the most important point. How these references move around the code, the most important thing to understand. How these references move around our code. If you don't understand that, it's really easy to write buggy code that doesn't do what you expect it to do if you're not understanding how your references move around. I know because I used to write buggy code like that until I finally understood references. But when we get to p1.setName, now we're going to see the calling object thing. So far, it's always been this dot. This is the first variable dot. So p1 dot means follow the reference, dot. And then from this object here, OX999, we're calling setName. So we're calling setName from this object. So this is the calling object. So inside that stack frame, this is going to be OX999. So we get this method called for setName. This is OX999. We're going to update the name variable. This dot name equals name. This dot name equals name. And that updates to Paladin. In the next line, we call getName through P3. When we call P3.getName, P3.getName, we're calling from the same object. This is 999. We return this dot name, which is updated to Paladin. When we set the name of P1, we can see that change through P3. So if you don't understand references, you're like, why did P3 change? We only changed P1. Well, it's because we do understand references and they refer to the same object. Two variables referring to the same object. When we set the name of P1, we see that change in P3. So P3's name changed because there is no P1 in P3. There's only OX999, and P1 and P3 both have references to that same object. There's only that object that they both refer to. And of course, the other object, this object didn't change at all. It's a completely different object that P2 refers to. This remains unchanged because we never went over to that space in the heap and called a method and called one of its setters. We never did anything with that object. Okay, questions. Quite a bit of new stuff. Mostly all the this moving around the code in references is and a constructor call are the real big new things. So questions. What's the point of having two different variables represent the same object? I don't know if I was ready for this question. In this example, not. I could still answer it, but it's a good question that I could talk about for a long time, but I wasn't ready for the whole thing. So let me try to give a TLDR of it. So in this example, there's no point. You just wouldn't do this. Why would I want two variables? I'm just going to use one variable, P1, and access it there. But the concept I want to show is that we can have two variables that refer to the same object. Where this is going to be important is through method calls. When we call a method that takes a reference to a player, understanding that we're only passing a reference to that player to that method, and that method can make changes to that object on the heap, and then after that method call ends, we can see that change that was made. So for example, if we just called p1.setName, we got rid of p3 and just called p1.setName and print p1.getName, even though setName returns void, it has a reference to the object. We assigned this by reference, and it followed that reference to the heap and made a change to that object, and we can see that change to P1, even though we never said P1.name equals something. We never did that, but the name of P1 did change. The state of P1 changed in a separate stack frame because that stack frame had a reference to that object. So when we start writing methods that take references to our objects, that's when we will use that extensively, having two variables of the same name, because those two variables will be in different stack frames. Having two variables in the same stack frame that refer to the same object isn't really useful, like we're doing here. But I'm just warming you up to passing references to methods. If we do P3 equals player of Dark Cecil 10, would it be the same effect as player P3 equal P1? I assume you mean new in there, P3 equals new player, and no, you would get a third object on the heap that would just happen to have the same values as this object at 999. You would get a third object if you create a new one. Without the keyword new, that doesn't compile. But I assume you meant new in there. Even if the values are identical, you will get a separate object if you call the constructor again. Java won't say, whoa, you just created an object with those same exact values. Let me just refer to that old one. Java won't do that for you. If you say new, you're getting a new object. End of story. New creates a new object. And Java isn't going to shortcut that for you, even if you want it to. When in our memory diagrams, why do we write this before the parameters? If you write this after your parameters, I'm not going to care. Like, you're not going to lose points for that. Me and Paul, that's just where we end up putting it. I don't know. It makes sense to me to put it there, but I can't explain why that makes sense to me. If you put it after your params, that's fine. If that's another thing where if you do end up losing credit for something like that, let me know. I'll fix that one. But the TAs, they shouldn't be taken off for that. Yeah.
If we're going to call another print statement, like P1 get name, is it still?
Yes. Yeah, so if I add another line to this program, say system.out.println P1.getName, it's going to go to the reference of P1, go over here, get the name, and it's still going to be Paladin. Yes. Any other questions before we jump into the next one? Or actually, I got a few wrap-up slides on this example, and then we'll jump into the next one. So I've mentioned this in passing quite a few times. Let's get a slide out on this and address it head on. So the only values that are stored directly in our variables, the only values that are assigned by value, passed by value, are our primitive types in Java. This is double, int, char, boolean. Those are the only 4 primitive types we've seen so far. Those are probably the only 4 we'll use in this class. There's really no need for us to use the other ones, but like long, byte, short are other ones. Float are ones that we just won't use in this class because we don't really need them. But those are the only values that are stored on the stack directly. Everything else, which is everything that starts with a capital letter or just anything, more specifically, anything that's not one of those primitives. So you technically can create a class that starts with a lowercase letter, even though you never, ever should. Everything else is stored in the heap and passed by reference and assigned by reference. So everything else, including every single class you'll ever write, whenever you write a class and create new objects of that type, those objects are on the heap, end of story. They're not primitive types. They go on the heap. So everything's going on the heap except those couple of exceptions. And a couple of exceptions that we're going to throw in there just for 116, again, for the sake of simplicity, so we're not getting buried and lost in details that are irrelevant to the learning objectives of this course. We are going to pretend that strings and our boxed primitive types are also passed by value, assigned by value, and are stored directly in our variables by value. Part of the reason of this is that's exactly why they behave. I just mentioned this for strings a few slides ago. Strings behave exactly like they're passed by value because they're immutable types. Whenever you change a string, you cannot actually change it. What you get is a copy of that string with the change applied. So in effect, what happens is strings behave as though they're passed by value. When you're programming, if you pretend strings are passed by value, you'll be completely fine with that. So we're going to pretend they are in our memory diagrams, just so every time we have a string or change a string, every time you change a string, you'd have to create a new object on the heap. It would just get tedious as hell. Technically, the string would have a reference to an array also, so you'd be drawing 2 separate objects every time you change a string or have a string primitive in your code. We're not doing that. It's just too distracting from what we want to do. We're going to pretend that they just are stored right in our variables by value and not by reference, even though they are actually stored by reference and passed by reference. Same with our autobox types. We're not going to treat double with a capital D different than double with a lowercase d. We're just going to pretend that our capital D double auto boxed class for that primitive, we're just going to pretend that those are passed by value as well, even though they're technically not. But they are immutable just like strings, so they behave the same way. And then the last one, there are compilers in the JVM are very complex, sophisticated programs. Sometimes they might put things that we expect to be on the heap in the stack and vice versa. They might do things, strange things, in the name of optimization and performance. We're going to pretend that it doesn't do that in our memory diagrams, just to keep things simple. There's no reason in 1.16 to say, well, on this quiz, we're going to use version 15 of this Java compiler. On this quiz, it's version 16. You have to know the difference. No, we're just going to stick with the actual theory, the computer science concepts on our slides, and forget about specific implementations of different versions of different pieces of software and compilers and stuff. We're going to ignore all that. But there are cases where the compiler might optimize and put things in different places in memory in the name of optimization. So those are all my disclaimers on our memory diagrams. I think for the rest of the semester, I think those are the only times we're going to violate reality in our memory diagrams. When we print out one of our objects to the screen, we have our player class, and I create my player P1, and I just want to print out P1. What do I get? Well, I get garbage. I'm going to get the fully qualified name of that type, which is the package name and the class name, an @ symbol, and then some random to us hex value, which is going to be somewhat the reference. It's not exactly the reference, but it's going to represent a reference to that object. This is what I got when I ran this code. If you run it, you'll get something similar, but the hex value will be different based on where how your JVM is storing that value. This is almost always not what we want. In this class, it's never what we want. I've never had a case where this was what I wanted, actually. So this isn't what you want. So how do we get something meaningful printed to the screen? We're going to write a toString method. If you write this is another special method that has to have this exact signature. We've seen a couple of these, main and our constructors. There's a certain convention you have to follow before Java treats it as a main method or as a constructor. Same with toString. This method has to be called toString in camel case and return a string. And if it does, then when you print your value to the screen, the system.out.println will actually call toString on your object before printing it. So whatever string you return from toString, that's how your object will be printed to the screen. So if you want some more meaningful output when you print your values to the screen, this can be very helpful, especially in debugging. But also if you're displaying information to a user and you want it in a more human-readable format, it helps to override this to write this toString method and return something that's meaningful to your specific application. I think printing out the current health of the player makes sense. We could also print out the name if we wanted to, but at least printing out the health is helpful. More helpful than what we get by default, at the very least. And now that we defined a brand new type, classes define types. We have a player type now, and we can use that type wherever we could use any other type in Java. We've already seen this in variables. We have variables of type player that store references to player objects on the heap. But we can also have methods that take player references as parameters, and also methods that return players and data structures that store players. We can have all those things. So if we want players to be able to attack each other, we write an attack method that takes a player and then damages that other player. Very much something we can do. I'm not going to trace through this code in a memory diagram because I want to get to the next example, which will show the same idea here. But more, I guess. I don't know. But any questions on player before we move on to that next example, which is going to be the party example? Any other questions on player? Let's do it. Okay, let's go on to the next one. There's not too much new in this one. It's mostly reinforcing the things we've seen been seeing since Monday, and we're going to see it in a memory diagram. But there are two things I want to highlight: composition and garbage collection. Composition is a big fancy word that means here's something you already know, but and I'm usually not big on vocab, but I'm starting to sprinkle in more vocab in my slides. Composition is whenever you have an instance variable that itself is a reference to another object. So we say that the party class is composed of an array list of characters because it has an array list of characters as one of its instance variables. So we're creating an object on the heap, which itself stores a reference to another object on the heap. When that happens, we call it composition because we have to have a fancy word for everything, and it frustrates me, but we have to have this fancy word, composition. It's not that fancy, I guess, but it's fancier than it has to be. We can just say, yeah, of course, that's a type in Java, so of course that's a variable. The variable can have that type. I don't think we need a new word for it, but here we are. And the next thing, garbage collection. Whenever we have, this one is important and more meaningfully named, I think. It collects the garbage. Easy. Whenever we have an object in the heap where we no longer have a reference to that object in memory, so we can no longer access that object is a prime candidate for what's called garbage collection. That means the JVM is going to, at its leisure, delete that object from memory. If we don't have a reference to an object anywhere in memory, we cannot access that value. So Java's going to say, hey, you can't even get to this. What are you doing? Let me take this memory, reclaim it, and give it back to the operating system, or keep it for the JVM for another Java program. It's going to reclaim that memory and take it away from you. Because it might as well not exist, because we lost the reference to it. We can't access it anymore. So that's the first thing we'll see in the memory diagram, is a little bit of garbage collection. Let's get to it. So creating the character, we've seen some constructor calls by now, so I won't belabor this point. But I want to highlight the differences here. This character has the default constructor. For what it's worth, if I didn't declare a constructor at all, this is what I would get. The default constructor, no parameters, no code in the constructor. I would get this one. To be explicit, I'm going to add it explicitly to show that, I meant to use the default constructor. I like to be explicit in my code. And then we have two instance variables that are both initialized to 0, and they're initialized outside of the constructor, so every character that's created will have these variables start at 0 and 0. So we get our character 0 and 0. Again, if you don't have the 0 here, I think I mentioned this earlier in this lecture. If I don't have the 0 here, I'll get the default value for an int. If you create a variable in Java but don't initialize it to anything, you'll get the default value for that type. For an int, the default value is 0. So if I left off this equals 0, I would get the same effect here. But again, I want to be explicit in my code. If I say equals 0, nobody has to question, like, wait, did he mean to use the default value, or did he just forget to initialize these? I put equals 0 there, and there's no question at all. I meant to initialize them to 0. Just makes my code easier to read and just more clear what my intent is when somebody's reading this code. And then immediately, we're going to set hero equal to a new character class. So we see the keyword new again. We're going to create another new object. That object goes on the heap. It returns a reference. Hero stores a reference to that object that was created. It replaces the old reference. And hero now refers to that second character that was created. Now, this isn't something you would ever do in your code, just like a lot of these lecture examples. I'm just warming you up to get to the other stuff. Just showing you the concepts in a simplified way, I guess. You would never do this, create a variable, assign it to a new object, and then immediately replace the reference to that object. But I just want to show garbage collection. So you wouldn't actually do this. Just like the last example. You wouldn't actually do P3 equals P1. But this is an example of garbage collection. We can't access that first character anymore. Once we hit this line of code, once we execute this and replace the value in hero, this 875 reference no longer exists in memory. It was replaced and overwritten by 320. We no longer have a reference to 875 in memory. So we can't access that object. Our reference is like our roadmap. This is how we find the object in memory. If we burn all those roadmaps and throw them away so we can't access them anymore, we can't access that object anymore. We have no way of accessing that. No matter what code I write after this line, I can't write any code at all that will ever access that first character for which we've lost the reference to. We can't access it anymore. So Java says, hey, you can't even access this anymore. We're getting rid of it. And in our memory diagrams, we're going to denote that by just Xing it out. That object no longer exists in memory. It's going to be garbage collected. So we're going to cross it out to show, yeah, we can't access that anymore. We lost it, got garbage collected, or it will get garbage collected. Java, we have very little control over garbage collection. Java just does it at its leisure. But it's a candidate for garbage collection, so in our memory diagrams, X it out. We're going to create a third character. This time we're not going to reassign hero. We're going to create another variable for it, so we have access to these two characters that we'll work with for the rest of the example. Hero.winBattle. Hero.winBattle. So this character is calling the method. So this character is this in the stack frame. So 320 is this in the stack frame. XP is 10. Okay, I did that slide again. I did that last lecture too. And then we're going to update our values. This.battles1, increment it by 1. So we're in this stack frame right now. This.battles1, increment. This.xp, increase by xp, which is 10. So we get those values updated. Now notice that this method has a return type void. It doesn't return anything, but it did change the state of our program by changing the state of one of our objects. This state changed in this object. So even though this method didn't return anything, we don't have a return arrow, it didn't do anything with the return value, nothing with that. But it did have an effect called a side effect, which is why we called the method. We called this method for its side effect of changing an object, the state of an object on the heap. So it did affect our program even though it didn't have a return type. Even though it had a return type void and didn't return any value. Didn't have a return value. Any questions? Should get music in a second. And party is where I want to stop because there's no way I can explain all this in the 1 minute we have left. Any questions before the music starts? Maybe I'll explain party in 10 seconds.